star explodes. For a few weeks, it can rival the light of an entire galaxy. Then the light fades, the gas drifts apart, and the sky goes quiet again. That is the story we tell about how stars end. A flash, and then nothing. But when astronomers go back and look at the wreckage, they keep finding something they did not expect. Something is still there. Sometimes it is a scarred, half-burned white dwarf, still glowing where it should have been vaporized. Sometimes it is a star flung out of the blast so hard it will leave the galaxy forever. Sometimes it is a spinning corpse that fires a beam of radiation at us hundreds of times every second. And sometimes it is something so magnetically violent that it can reach across 50,000 light years and disturb the atmosphere of our own planet. None of these things are alive, not in any way that matters to a physicist, but almost none of them are finished either, which raises a question that turns out to be much harder than it sounds. What does it actually mean for a star to die? Stars that survive their own explosions. To understand why survival is strange, you first have to understand what is supposed to happen. Most stars in the universe will end relatively quietly. They will swell, shed their outer layers, and leave behind a dense cooling core called a white dwarf. That is not a supernova. It is exhaustion. It is also the broad fate expected for our own sun in about 5 billion years. White dwarfs can meet a more violent end inside binary systems. In one possible pathway, a white dwarf accretes matter from a companion until conditions trigger a runaway thermonuclear reaction. In another, two white dwarfs merge. Astronomers still debate which pathways dominate the normal Type 1a population. To understand why survival is strange, you first have to understand what is supposed to happen. Most stars in the universe will end relatively quietly. They will swell, shed their outer layers, and leave behind a dense, cooling core called a white dwarf. That is not a supernova. It is exhaustion. It is also the broad fate expected for our own sun in about 5 billion years. White dwarfs can meet a more violent end inside binary systems. In one possible pathway, a white dwarf accretes matter from a companion until conditions trigger a runaway thermonuclear reaction. In another, two white dwarfs merge. Astronomers still debate which pathways dominate the normal Type 1a population. They looked like Type 1a supernovae in their spectra, but they were too faint, too slow, too weak. Not by a small margin. Some of them released only a fraction of the energy they should have. Astronomers gave this class a name, Type 1ax. One leading explanation for why many of them are so weak is unsettling. In that model, the runaway reaction starts, tears through part of the star, and then stalls. The explosion fails to finish the job. The star is blown open, violently, but it is not fully unbound, which means something is left behind. Informally, astronomers started calling these leftovers zombie stars. That phrase needs a warning label, and it is worth being precise about it. Zombie star is a nickname. It is journalistic shorthand, not a formal scientific classification. There is no category in astronomy called a zombie star. What the term is pointing at is a real and technical idea, the bound remnant of a partially disrupted white dwarf. But the word is doing emotional work, not scientific work, and it is worth keeping those two things separate. The most famous example arrived in 2012. In the spiral galaxy N, GC 1309, about 110 million light-years away, a supernova appeared. It was catalogued as SN2012Z, and astronomers got extraordinarily lucky. because the Hubble Space Telescope had already photographed that exact patch of that exact galaxy, repeatedly, for years before the explosion. That almost never happens. Normally, a supernova is a surprise, and the star that produced it is gone before anyone thought to look at it. When Curtis McCulley, then a graduate student at Rutgers, sharpened those pre-explosion images, he found something at the location, a source that should have been far too faint to see. The interpretation was a white dwarf paired with a blue helium companion, a system where the dwarf had been feeding off its neighbor until the reaction ignited. That alone was a significant result. It was one of the few times astronomers have identified the star system that produced a thermonuclear supernova before it exploded. But the stranger part came later. When Hubble returned to NGC 1309 years after the explosion, a source was still present at the position. And based on those observations, researchers reported that it appeared brighter than the progenitor system had been before the supernova. Think about that for a moment. The explosion should have erased it. Instead, the interpretation is that something survived and was left hotter and more luminous than it started. The physical explanation, if the model is right, is that the failed explosion dumped enormous energy into the surviving remnant without unbinding it. The star was left puffed up and glowing from the injury. It is not thriving. It is a wound, radiating. We should be careful here, and the researchers themselves are careful, disentangling a surviving remnant from its companion star and from the fading light of the supernova itself at a distance of 110 million light-years is genuinely difficult. This is an interpretation supported by observation, not a photograph of a survivor. The field is still working on it, but there is a second case, and this one is in our own galaxy. In August of 1181, astronomers in China and Japan recorded a new star near the constellation Cassiopeia. They called it a guest star. It stayed for about 6 months, then faded, and for more than 800 years, nobody could find where it had been. It became one of only a handful of supernovae in recorded human history, and the only one that had no known remnant. Astronomers called it an orphan. Then, in 2013, an amateur astronomer named Dana Patrick, working through archived data from NASA's WISE telescope as part of a citizen science project, found a faint nebula. He thought it was a planetary nebula. It was his 30th find, so it was catalogued PA30. It was not a planetary nebula. In 2021, researchers linked PA30 to the guest star of 1181, and at its center is a star that should not be there. The central object is one of the hottest stellar surfaces known in our galaxy. Measurements place it at roughly 200,000 Kelvin. It is blasting a wind outward at extraordinary speed. Published measurements report outflow velocities in excess of 15,000 kilometers per second. Its spectrum shows no hydrogen and no helium at all. X-ray observations of the surrounding nebula found the ashes of carbon burning. That combination is very hard to explain with an ordinary star. It looks like the exposed, shredded interior of something that went through a thermonuclear event and did not finish being destroyed. In 2024, a team led by Tim Cunningham at the Center for Astrophysics used the Keck Cosmic Web Imager to map the nebula in 3 dimensions. What they found looks nothing like a normal supernova remnant. Instead of a smooth, expanding shell, PAR 30 has narrow filaments radiating outward like the seed head of a dandelion, moving at around 1,000 kilometers per second. The measured motions are consistent with nearly ballistic expansion, close to free expansion, with little evidence that the filaments have been strongly decelerated. That means astronomers can run their paths backwards, take the measured velocity, take the direction, and estimate when the material was launched. The result lands close to the year 1181. An amateur astronomer's archival hunch, a citizen science project, and a 1,000-year-old Chinese and Japanese record all converged on the same object. There is still real uncertainty about what exactly happened here. One proposed model is a partial deflagration of a single massive white dwarf. Another, argued by Bradley Schaefer, is a collision between two white dwarfs, one carbon-oxygen, one oxygen-neon, leaving a merged remnant. There is also an inner void around the central star that nobody fully expected, and questions about whether the infrared emission is dust or hot gas that may need the James Webb Telescope to settle. But the core of it is not in serious doubt. Something exploded there, and something is still sitting in the middle of it, screaming. This matters beyond the novelty. Type 1. A supernovae are one of the tools we use to measure the size and expansion of the universe. We rely on them being consistent, and yet, despite decades of work, astronomers still have not identified one progenitor pathway that explains the entire normal Type 1a population. These broken, incomplete explosions may offer one of the clearest views of the machinery. The failures are teaching us how the successes work. Survivors thrown across the galaxy. If an explosion can leave a star behind, it can also throw one. Picture a white dwarf and a companion locked in a tight binary, whipping around each other at enormous speed. That orbital motion is like a stone in a sling. As long as both stars are there, gravity holds the system together. Now remove one of them, instantly. If a supernova destroys or partially disrupts one member of that pair, the gravitational anchor vanishes. Whatever survives keeps the velocity it already had, and it leaves, not drifting, fired. About 630 parsecs from the Sun, roughly 2,000 light-years, there is a star doing exactly that. It is called LP 40-365, also catalogued as GD 492. It is one of the strangest objects in the catalogue. Start with what it is made of. Its atmosphere has no detectable hydrogen and no detectable helium in the original analysis. Instead, it is dominated by oxygen and neon, and it is loaded with heavy elements: sulfur, chromium, manganese, titanium, iron group material. These are not the elements a normal star wears on its surface. These are the products of nuclear burning. This is not a star's skin. This is its cooked interior, turned inside out. One measurement in particular stands out. The manganese to iron ratio is around 7 times higher than the Sun's. That specific signature is a strong pointer, because it matches theoretical predictions for a thermonuclear explosion in a white dwarf near the Chandrasekhar mass limit. There is a second clue in its size. Using precise parallax data from the Gaia mission, researchers estimated its radius at about 18/100ths of the Sun's radius. That is roughly 10 times larger than a normal white dwarf. It is puffed up, inflated, consistent with a star that was violently heated and has not yet settled back down. And then there is how it is moving. LP 40-365 has a rest frame velocity of approximately 850 kilometers per second. That is fast enough to escape the Milky Way's gravity entirely. It is not orbiting our galaxy. It is leaving it permanently, and it is never coming back. Here is where a crucial distinction has to be made. because it is easy to blur. There is a separate, better-known class of objects called hypervelocity stars. Those are usually ordinary stars, real, fusing, living stars that have been flung outward at extreme speed. The leading explanation for many of them involves the supermassive black hole at the center of our galaxy, Sagittarius A star. If a binary pair of stars wanders too close, the black hole's tidal forces can capture one and slingshot the other outward at enormous velocity. LP 40-365 is not that. Researchers traced its trajectory backwards through the Milky Way's gravitational field and found that it crossed the galactic disk roughly 5 million years ago, in the direction of the constellation Carina, at a distance of about 6.5 kiloparsecs from the galactic center. It did not come from the center. It almost certainly has nothing to do with the black hole. So there are at least two completely different ways to launch a star across a galaxy. One involves a black hole acting as a slingshot. The other involves a supernova acting as a detonator inside a binary system. They produce superficially similar results, a star moving impossibly fast, and completely different objects. There is also a third population worth knowing about, discovered using Gaia data. They are called D6 stars, and they move even faster, above 1,000 kilometers per second. Those are interpreted as the surviving donor stars in double white dwarf systems, where one member detonated. Not the exploded star, the one that was standing next to it, which gives you three distinct kinds of survivor. The star that was thrown by a black hole, the star that was standing beside a bomb, and the star that was the bomb and lived. LP 40-365 appears to be the third. There is a rotation measurement of about 8.9 hours that researchers used to argue it was most likely the bound remnant of a mostly disrupted white dwarf, rather than the donor, and it is worth sitting with what that means. If the interpretation holds, this object was at the center of a thermonuclear explosion. It was blown apart badly enough to expose its own nuclear ashes to open space, and its response to that was to survive and to run. Its present motion places it on an escape trajectory from the Milky Way. Over immense spans of time, it will carry the chemical signature of the explosion that nearly destroyed it into intergalactic space. Dead stars that still speak. Everything so far has been about white dwarfs, the quiet endings, and the explosions that go wrong. Now we go to the other extreme, because when a genuinely massive star runs out of fuel, the ending is not gentle, and what it leaves behind is not quiet at all. A star stays stable through a standoff. Gravity pulls inward, trying to crush it. The heat and pressure from fusion in the core push outward. For millions of years, those forces are matched, and the star holds its shape. Fusion is the star fighting gravity, and it is a fight the star cannot win forever, because fusion needs fuel, and fuel runs out. When the core of a massive star finally stops producing energy, the standoff ends instantly. There is nothing left holding the weight up. The core collapses, and it collapses fast, in a fraction of a second. The pressure is so extreme that atoms themselves stop working. Electrons are driven into protons. What comes out the other side is a sphere made mostly of neutrons, compressed to densities comparable to those inside an atomic nucleus. A neutron star. The numbers here are the kind that stop meaning anything if you say them too fast, so let us go slowly. Take more mass than our entire sun. Compress it into a ball roughly 20 kilometers across, a city. The material is so dense that a single teaspoon of it would weigh something on the order of 1 billion tons on Earth. Not a metaphor, a teaspoon. And these objects are not inert. They spin. The reason is simple physics. When a spinning object shrinks, it spins faster. A figure skater pulls their arms in and accelerates. Now take a stellar core, already rotating, and collapse it to the size of a city. It comes out spinning astonishingly fast. It also carries a ferocious magnetic field, and that field is not necessarily aligned with the rotation axis. So the neutron star fires beams of radiation out of its magnetic poles, and those beams sweep around the sky as the star turns, like a lighthouse. If one of those beams happens to cross Earth, we detect a pulse, then nothing, then another pulse, at exactly the same interval, over and over. We call them pulsars. They do not actually blink. The emission is essentially continuous. We only see a pulse because the beam is rotating past us. What we are detecting is not the star flashing. It is the star turning. When Jocelyn Bell Burnell first found one of these signals in 1967, its regularity was so unnatural that the possibility of an artificial origin was briefly, half-jokingly entertained. It was labelled LGM1, Little Green Men. It was not aliens, it was a corpse, keeping time. And pulsars have turned out to be one of the most useful instruments in astronomy. Their timing is so stable that they function as natural clocks scattered across the galaxy. They have been used to test general relativity, to detect the first known planets outside our solar system, and to search for gravitational waves rippling through the fabric of space. The most extreme example known sits about 18,000 light-years away in a globular cluster. Its catalogue designation is PSR J1748-2446ad. It rotates approximately 716 times every second. That is not a typo, and it is worth pausing on rather than rushing past. 716 full rotations. In 1 second, an object with more mass than the Sun, turning faster than a kitchen blender. From that measured rotation rate and an estimated radius, scientists infer that the surface at its equator is moving at a substantial fraction of the speed of light. Estimates commonly cited are in the range of 1/5 to 1/4 of light speed. That inference deserves an honest caveat. The rotation rate is measured, and measured with extraordinary precision. Pulsar timing is one of the most accurate measurements in all of science. The equatorial speed is derived. It depends on the star's radius, and neutron star radii are not directly measured. They are constrained by models and by the still uncertain physics of matter at nuclear density. So treat the rotation as fact, and the surface speed as a well-motivated estimate. The obvious question is why it does not simply tear itself apart. Anything spinning that fast should fly to pieces. The answer is that its gravity is winning. The gravitational binding at the surface of a neutron star is so overwhelming that it holds the star together against a centrifugal force that would shred any ordinary object instantly. There is a limit. Spin a neutron star fast enough and it would break up. But this one is not at it. Fusion stopped in that object a long time ago. By any working definition, it is dead. It is also one of the most precise natural clocks known. Magnetars. The magnetic monsters. Some neutron stars are worse. A magnetar is a neutron star, but with a magnetic field so extreme it stops being a property of the star and becomes the dominant force in its existence. The distinction matters. A standard pulsar is powered by rotation. It spins, it drags its magnetic field around with it, it radiates, and it very gradually slows down. Its energy budget is its spin. A magnetar is powered by magnetism itself. The field is the fuel. and that changes everything about how it behaves. The field strengths involved are difficult to convey. Earth's magnetic field is around half a Gauss, enough to turn a compass needle. An ordinary neutron star might reach 1 trillion Gauss, already far beyond anything achievable in a laboratory. A magnetar can reach on the order of 1,000 trillion Gauss. NASA has described a field that's strong as capable of wiping the magnetic strip on a credit card from halfway to the moon. That field is not stable. It is wound up, strained, and it is trapped inside a rigid crust. Because a neutron star has a crust, it is not a fluid ball. It is thought to have a solid outer shell, crystalline, and by some estimates enormously stronger than steel. And that crust is being twisted from beneath by a magnetic field that will not sit still. Eventually, the crust gives. It cracks. The star fractures. Scientists call these events starquakes, and the term is more literal than it sounds. The fracture is minuscule. The energy released is not. When the crust shifts, the magnetic field lines anchored in it are forced to rearrange. That reconfiguration dumps a colossal amount of stored magnetic energy into space almost instantly as X-rays and gamma rays. Most of the time, these are short bursts. Rarely, extremely rarely, a magnetar does something far worse. On the 27th of December 2004, a magnetar called SGR 1806-20 emitted a giant flare. It was the third such event ever recorded. The published total isotropic energy of the flare is around 2 × 10⁻46 ergs, which the discovery paper notes is roughly 100 times more energetic than the 2 previously observed giant flares. The energy release is attributed to a catastrophic reconfiguration of the star's magnetic field. SGR 1806-20 is on the far side of our galaxy. Distance estimates in the literature vary considerably, but it is on the order of tens of thousands of light-years away. From that distance, across the entire width of the Milky Way, the flare saturated the X-ray and gamma-ray detectors on multiple spacecraft, instruments that were not pointed at it, and it produced a measurable disturbance in the ionosphere of the Earth. A dead star, tens of thousands of light-years away, physically perturbed the upper atmosphere of our planet. In the days that followed, radio telescopes watched an expanding nebula of material blown off the magnetar, moving outward at a substantial fraction of the speed of light. This is the part that should reorganize how you think about stellar death. Whatever star produced SGR 1806-20 was massive enough to collapse. Its death concentrated an enormous reservoir of rotational and magnetic energy into a remnant only about the size of a city. That remnant is capable of outbursts the original star could never have produced in the same way. The end of fusion did not reduce this object's capacity for violence. It concentrated it. There is one more thread here, and it needs to be handled carefully. Fast radio bursts are millisecond-long blasts of radio energy arriving from across the universe, and their origin has been a major open question. In 2020, a burst was detected from a magnetar inside our own galaxy, SGR 1935+2-154. The first time an FRB-like signal was linked to a known object. That was a genuine breakthrough. It established that magnetars can produce these signals. It did not establish that magnetars produce all of them. The known population of fast radio bursts is diverse. Some repeat, some do not, and their energies span an enormous range. Magnetars are now a confirmed source of at least some FRB-like emission. Whether they explain the whole population remains an open question, and anyone who tells you it is settled is going beyond the evidence. Stars that erupt again and again. So far, survival has meant surviving once. Some stars have made a habit of it. Return to a white dwarf with a companion. But this time, change the details slightly. The dwarf is pulling hydrogen off its neighbor, and that hydrogen is piling up on its surface. The white dwarf's gravity compresses that stolen layer relentlessly. Pressure builds, temperature builds, and at a critical point, the accumulated hydrogen ignites in a runaway fusion reaction across the entire surface of the star. The star brightens by an enormous factor, sometimes appearing where nothing was visible before. Historically, that is exactly what people saw. A new star appearing in the sky, which is how the phenomenon got its name. Nova, new. But here is the crucial part, and it is the difference between a nova and a supernova. In a nova, only the accumulated surface layer undergoes a thermonuclear runaway. The white dwarf underneath survives, although repeated eruptions can alter its mass and long-term evolution. The explosion throws much of the accumulated material into space, and the binary system carries on. And if the companion is still there, it starts again. It resumes stealing. The layer rebuilds, pressure climbs, and eventually it happens again. These are recurrent novae, and some of them have been observed erupting multiple times within a single human lifetime. The distinction from a supernova is not merely one of brightness. A nova is a surface eruption in a binary system, a normal type 1. A supernova disrupts the exploding white dwarf. A nova can recur while mass transfer continues. It is not the death of the star. A white dwarf binary can erupt as a nova again and again. The system survives each recorded outburst, even though its long-term fate may eventually be very different. Which brings us to the star everybody is watching. Betelgeuse sits in the constellation Orion, roughly 500 to 700 light-years away. The distance itself is not precisely pinned down. It is a red supergiant, and it is unmistakably near the end of its life. When it explodes, it is expected to be visible in daylight, and in late 2019, it started going out. Betelgeuse had been known for over a century to vary in brightness on a roughly 400-day cycle. This was not that. Starting around October 2019, it began fading dramatically, and by mid-February 2020, it was the faintest it had been in nearly 2 centuries of recorded observation. It had lost a substantial fraction of its brilliance, enough to be obvious to the naked eye, to anyone who knew Orion. The speculation was immediate and obvious. Was this the beginning of the end? It was not. But what it actually was turned out to be more interesting. Observations led by Andrea Dupree at the Center for Astrophysics, using Hubble's ultraviolet spectroscopy alongside multiple other observatories, assembled a timeline. Between roughly January and March of 2019, a shock moved through the star's photosphere. Through September to November of 2019, Hubble measured material moving outward from the surface into the outer atmosphere at speeds of around 200,000 miles per hour. The interpretation is that a vigorous convective cell, a rising bubble of hot plasma from inside the star, drove a substantial mass of material off the surface entirely. The published term is a surface mass ejection. We have seen coronal mass ejections from our own sun. This was the same idea, scaled to something monstrous. The ejected material travelled out beyond the visible surface, cooled, and condensed into dust. That dust cloud then blocked light from a significant portion of the star's disk, as seen from Earth. Betelgeuse did not dim because it was dying. It dimmed because it threw a piece of itself into space, and the debris got in the way. The aftermath is arguably stranger than the event. The paper reports that afterwards, the photosphere was left cooler, the chromosphere less dense, and, remarkably, the star's steady 400-day pulsation, a rhythm that had been observed for well over a century, disappeared for more than 2 years. The star lurched, and its heartbeat stopped keeping time. Now, the question everyone asks, when does it explode? Nobody knows. And it is important to be honest about the shape of that uncertainty, rather than hiding behind it. Betelgeuse will end as a core collapse supernova. That much is not seriously disputed. But the timescale is not predictable with current methods. It could be tens of thousands of years, or longer. On stellar timescales, that counts as imminent. On human timescales, it is effectively never. The Great Dimming was not a countdown. It was a star being messy. Betelgeuse has delivered another surprise. In 2026, Hubble and ground-based observations found firm evidence for a low-mass companion called Siwaha, moving through the star's extended atmosphere and leaving a dense wake. That companion helps explain Betelgeuse's longer, roughly 210-day cycle and some of the changes seen in its outer atmosphere. It does not mean the star is about to explode, and it is not the main explanation for the Great Dimming. And there is one final possibility, which forces us to question the premise of the whole subject. We assume that a massive star dying means an explosion, but models have suggested for years that a fraction of core collapses may not produce a bright supernova at all. Instead, the core collapses, a black hole forms, and the star is simply swallowed by its own remnant, with little or nothing to see. A failed supernova, a star that vanishes. The most discussed candidate is an object in the galaxy NGC 6946, designated N6946-BH1. A massive luminous star underwent an outburst in 2009, then faded dramatically in the optical and did not come back. Searches with the Large Binocular Telescope found no star where a star had been. For years, it stood as the leading candidate for a direct collapse to a black hole. Then JWST looked at it, and the story got complicated rather than resolved. Observations led by Emma Bowser, published in 2024, showed that what everyone had been treating as a single object is actually a blend of at least 3 sources. An infrared source remains at the position, at roughly 13 to 25% of the progenitor's luminosity. That study found that both a failed supernova and a dusty stellar merger or outburst could fit important parts of the data. The interpretation has continued to evolve. A 2026 reanalysis argued that the remaining source is much fainter than typical late-time merger remnants and can be modeled as a heavily obscured source, strengthening the failed supernova case. But that work does not yet amount to a direct detection of a newly formed black hole, and the debate is not closed. A dedicated JWST follow-up program is intended to monitor the source and obtain mid-infrared spectroscopy. The logic is elegant. If the near-infrared flux keeps fading, that would strengthen the black hole interpretation. If it remains steady or brightens while the mid-infrared fades, that would support a merger whose dust is clearing. We do not know yet which explanation will survive. We may be looking at one of the best candidates for a star collapsing into a black hole without a bright supernova. Or we may be looking at a stellar merger hidden behind its own debris. Either way, one of the most basic assumptions, that a massive star's death is a visible event, may not always hold. Some stars might not go out with a bang, They might simply stop being there. What star death really means. So let us try to answer the question we opened with. First, we need to be precise about what astronomers actually mean by a dead star, because the phrase is misleading. It does not mean cold. It does not mean inert. It does not mean gone. It means sustained fusion in the core has ended. That is the whole definition. The star has stopped generating energy by fusing elements in its center. That is the line between a living star and a stellar remnant. Notice what that definition does not require. It does not require the object to be dark. It does not require it to be quiet. It does not require it to be still. A white dwarf can glow for billions of years after ordinary sustained core fusion has ended. Par 30's central remnant is not an ordinary hydrogen-fusing star, yet it sits at roughly 200,000 Kelvin and drives an extraordinary wind. SGR 1806-20 is a compact remnant, and in 2004 it disturbed Earth's upper atmosphere from across the galaxy. Dead does not mean finished. It means the fire in the middle has gone out. So, the endings. Low and intermediate mass stars like the Sun generally end as white dwarfs. They shed their outer layers, and the exposed core remains, Earth-sized, extraordinarily dense, cooling slowly over timescales longer than the current age of the universe. That is the most common ending. It is also our Sun's future. If a star is considerably more massive, its core may collapse and leave a neutron star. City-sized, compressed to roughly nuclear densities, often spinning rapidly and carrying an enormous magnetic field. And here is a point worth being exact about, because popular accounts routinely get it wrong. Pulsars and magnetars are not separate basic remnant categories. They are both neutron stars. A rotation-powered pulsar is detected through beams that sweep past Earth, while a magnetar is defined by an extraordinarily strong magnetic field, whose decay powers much of its activity. The labels describe different observed behavior and energy sources, and the categories can overlap. Some neutron stars may never be detected as pulsars simply because their beams do not cross Earth. The universe does not care whether we can see the lighthouse. The lighthouse is still turning. And if a star is more massive still, the collapse does not stop at neutron degeneracy. Nothing known can hold the weight. It continues and forms a black hole. A black hole is not a star. It is worth being firm on this, because the language misleads. It does not fuse. It does not shine. It has no surface. It is a region of space-time where gravity has closed over itself. Some black holes appear to be among the brightest objects in the universe. Quasars can outshine entire galaxies. But that light is not coming from the black hole. It is coming from matter outside it, heated to enormous temperatures as it spirals in. The black hole itself contributes nothing to that glow. It is the thing the light is falling into. The brightest objects we can see are lit by the darkest. Now look back at what we have met. A shattered white dwarf in NG C1309 that appears to have come through a failed detonation brighter than it went in. A remnant at the heart of Par 30, still radiating at roughly 200,000 Kelvin, still throwing filaments outward, still traceable back to a single night in 1181 that was written down by people who had no idea what they were watching. LP40-365, wearing its own nuclear ashes on its surface, leaving the galaxy at 850 kilometers per second, never to return. A neutron star turning 716 times a second, keeping better time than most clocks ever built. a magnetar whose crust cracked and briefly touched our sky from across the galaxy. White dwarfs erupting again and again and again and surviving every time. And Betelgeuse throwing pieces of itself into the dark, unpredictable and unfinished. So when does a star truly end? Not at the explosion. Some of them walk out of that. Not when fusion stops. Some of them get louder afterwards. Perhaps the honest answer is that stars do not end the way we want them to. We want a clean line. Alive, then dead. The universe does not provide one. It provides a long, slow, extraordinarily violent transition between one kind of existence and another. Some become embers, cooling for longer than the universe has so far existed. Some become lighthouses, turning in the dark, marking time for nobody. Some become magnetic monsters, capable of things they could never do while they lived. Some are thrown out of the galaxy entirely, carrying the evidence of their own destruction with them. And a few, a strange, rare few, go through the explosion that was supposed to erase them completely and are still there afterwards, damaged, reshaped, unrecognizable, but still there. The fire goes out, and something remains in the dark that is not finished with the universe yet. Thank you so much for spending your time with Beyond the Surface. Your support truly means a lot to us. If this documentary inspired your curiosity, please like the video, subscribe to the channel, and share it with someone who also loves exploring the mysteries of the universe. Every like, comment, and share helps us continue creating more meaningful space documentaries for you.